This is AP1, review day 3. We're looking at circular motion, energy, and momentum. So the first thing that we need to understand about circular motion is there's different types. But the main one that we normally look at is this uniform circular motion. As long as it says uniform, that means that the speed is constant. Otherwise, it doesn't have to be, right? You can whirl something in a circle and this V could be greater up here and this V could be smaller down here. But if it says that it's uniform, right? If it says that it's uniform, then that means that this V, this V is equal to this V, right? No matter where you are in the circle. The velocity, of course, is changing, right? Because you're changing directions, because you change directions. And the acceleration and the force are always inward. So wherever my object is, my force and my acceleration are always inward. It's always perpendicular to the direction of travel. Important to remember that's always perpendicular to the direction of travel. And that force, the force is called centripetal force, right? We know that. You never label it on a free body diagram, right? You have to figure out what is causing the friction or the centripetal force. So it could be friction, it could be gravity. You would never label. So if I have an object, I would never say FC, unless it specifically says it, but I don't think it ever would. So just don't do that, right? Instead, you might have a free body diagram where this is F, and then you say, oh, well, F is equal to FC because that's the only thing holding it in a circle. Equations, the only equation they give you on the equation sheet, beware, is this AC equals V squared over R. They assume you know that F equals MA, and since if I put an M in front of this equation, it gives me FC equals MV squared. They assume that you already know that. This equation up here, this 2 pi r, is because we know circumference is equal to 2 pi r. And while they do give you that, you have to realize that 2 pi r is the distance it travels, and remember big T is the period, which is the time it takes to travel in one circle. So this equation is just V equals X over T in disguise, right? Big R, little r's don't matter. You can choose either one, but again, only that equation number 2 is given on the equation sheet. If you're looking at vertical versus horizontal circles, and remember, if you have it on a string, then we're looking at tension. If we have it on a track, then it's going to be N. So in this diagram, there is an object that's up here someplace, and it has 2 forces on it, and those 2 forces are going to be gravity, and the other force is going to be tension, right? Or normal force. It's not going to be FC, right? But if you look at those two, they're both pointing down. They're both pointing towards the inward. So that means FC is equal to T plus FG. And so my tension is going to be less, right? Because it's FC minus FG because gravity's helping, right? So gravity helps. That's the concept. Helps at that's an at symbol, the top. Right? When at the bottom, however, you still have T, right, pulling it up, and now FG is pulling it down. Well, they're pointing opposite ways. And so now you can see that FC is going to be equal to T minus FG because T is the one pulling it in and it has to fight against gravity. So now my tension is more, right? And so in this case, gravity is opposite FC at the bottom, right? That's the concept. So if it's gonna break, it's more likely to break at the bottom than it is to break at the top because tension's a lot more at the bottom than it is at the top of a vertical circle. For horizontal circles, the tension and normal force stay constant. Because they're just equal to FC and you don't have gravity helping or fighting against. Of course, in order to have, the only way to have a perfectly horizontal circle is you'd have to have like a marble on a table, right? So if you had like a table or something like this, and there was a hole in there, and then there was a marble like this, and the marble was going around like that, that's the only way to make a horizontal circle, right? And so it might be attached to a string like this, and then my T would be equal to FC in this case. But it wouldn't change if it's going in uniform circular motion. Work is a force that's applied over some distance. Remember that there has to be displacement and that the force must be in the direction of x. So technically it's W equals Fx cosine theta, but you're just looking for the component in the direction of the travel. So if x is going this way and my force is going this way, I only care, well, this was my force. I only care about this part of the force, right? Just this F of x part of the force is doing work over this amount of distance x, right? So you wouldn't multiply the whole force. If it's pointing the opposite way, right? If it's opposite, if F is opposite x, then it's negative work. And if F is perpendicular to x, then there's no work, right? So you have to pay attention to which way the force is relative to x. Remember, it's a scalar. We're not in vector line, which makes it nice. It can be positive, it can be negative, but it's a scalar, so you would never do cosine signs of work, right? You do it of the force because that's a vector. The work energy theorem says that work can change the energy of a system. So if you have an outside something doing work, either taking it away or giving you more, it can change it. So we have things like the change in kinetic energy can be equal to work, the change in potential energy can be equal to the work. And so you end up with delta mgh or mghf minus h naught, or 1/2 mv squared minus 1/2 mv squared. That will tell you how much work was done or how much you changed your energy, right? So it doesn't stay the same necessarily. The total energy of an object remains the same unless there's an outside force other than gravity. So that was something that people will get confused about because they're like, well, wait, gravity's acting on it, right? But gravity doesn't count because gravity's part of potential energy. So do realize that gravity is not going to count as doing work on it. It does do work on it, but it does it in the form of potential energy, so it's taken into account. And therefore, if you have work on the object, it changes the total energy. So some ways you can write it is you can write it as E naught is equal to EF. You can say K naught plus UG naught is equal to KF plus UGF, right? Friction is a force that decreases the energy, so you can subtract it from the initial or add it to the final, so the equation balances, so you end up with a negative Fx. So you can end up with an equation like work minus Fx. So that's how much energy I have because I had this amount of work, maybe I pushed it or something, and then I took away this amount of work because there was friction acting on it, and that's going to be equal to my change in kinetic energy plus my change in potential energy, right? Conversely, you could also say all the positive work. So I start with this, I start with work, I start with K naught, I start with UG naught, and I end up with the work of friction and my final kinetic energy and my final gravitational energy, right? So it depends on what you're doing for the problem, which one is easier. So just use logic to decide. It's the same equation. It's just which one's easier for the task. So this is kind of showing that again, right? If the work is added, then you can have it like this. There's no friction in that. If you have friction, you can put the friction on this side, right? Because the subtraction subtracts, so you can subtract it, etc. Power is the energy per time. It's how fast the work is done. So power is equal to W over T. Remember, the top W can be any type of joule. It says Q, but you don't know what Q is, so let's just ignore that one for now. But you can put anything in joules on the top. So it can be kinetic energy, it can be potential energy. So you could have power is equal to 1/2 mv squared, over T, right? You could have power is equal to mgh over t. Also remember, you do power is equal to F times V if you're going at the same speed the whole time. The way to realize this one is that this is Newton meters per second, and you can see that the units are still joules per second. And so this is one I always forget, so I like to point it out. But power is also equal to F times V if it's causing it to go at some constant velocity. You can figure out what the power of the force is causing. Momentum and impulse, so P is equal to mv, so if you're moving, you have momentum. I think this concept's pretty simple. Most of you seem to have done a pretty good job with it. It's always conserved if there's no outside net impulse. It's a vector, so it has direction, and sign are super important. So remember, this is always, the big thing is momentum's always conserved. Remember the bullet block video that I showed, and we all wanted to say, oh, conservation of energy, because that is so drilled into us. But the problem with all the different types of energy. But momentum, if you're dealing with linear momentum, there's only one type. It doesn't go away. It's got to be somewhere. So as soon as you hit something, its momentum is conserved. Now, of course, if there's friction and other things going on, you can take it away. But the moment things interact and hit, and if you see anything with collision, bouncing, explosions, your first frame of thought, your first thing should be, it's momentum. What's mv before? What's mv immediately after? Impulse is change in momentum, so that's J is equal to Ft, which is equal to m delta v. So I don't know why there's another equal sign over here. We don't really need that. But it's equal to the change in momentum. Remember, this is how Newton wrote it the first time. Because if you look at it and you solved it, right, you can see it's just F is equal to m delta V over T, which is ma, which is our good old friend from Newton that we saw the other day. F, remember, is impact force, so don't confuse force with impulse. They are not the same thing, because impulse is two things, right? It's the force and the time that force is applied, which causes a change in momentum. A force causes a change in velocity, right? So, they're related, and that's why it's easy to get them mixed up. If you have a big F, you're going to have a small t. If you have a big T, you're going to have a small f. So if you hit something really quick, like if you bounce or something like that, you have a small time, you're going to get a really big F. If you have something soft to land on, it's going to give you a really big T, so it's a smaller force. Never say because it's squishy, all right? Don't say because it's squishy. It's because it has a big time that force gets to act over. If there's no outside net impulses, then J is equal to 0, but not V. Remember, I keep saying this, I harp on it, because how many of you on the test tell me, oh, the impulse is gone, and so now it goes back to what it was before? No, it continues going on its merry way, whatever velocity ended up at. It's the highest, impulse is the highest if it bounces, because now it's going down with a positive V, goes up with a negative V, so your delta V is equal to 2V, and then it has a very small time, and so you have a big change in velocity over a small time. So this gives me between these two things, it gives me a huge impulse. Yeah. So anyways, remember that impulse. So types of interactions, always remember the total momentum before equals the total momentum after. But if it's an elastic collision, then the kinetic energy is conserved as well. They're not going to ask you to calculate like the velocity, knowing it's elastic collision and momentum is conserved, because it's a really nasty algebra. But you should be able to calculate the kinetic energy before and after and be able to say it is elastic or not elastic, if it's equal or not equal. So the three types of interactions, and of course all of these momentum is conserved with an explosion, sticky, and bouncy. With an explosion, the total momentum is 0. And so you have one thing going this way and one thing going this way. And it says Pi equals Pf. Well, that's always true, right? The initial is always the initial final. But if this is momentum of object 1 and this is momentum of object 2, they're equal but opposite. So if this has a tiny mass and this has a big mass, then this is going to have a big V and this is going to have a small v, right? Because they have to be equal. So that's kind of the concept. When it's sticky, then we think, oh, okay, so after we're going to stick them together to find the velocity before or the velocity, depending on what it was doing before. This would be not 1 and not 2 or something. Anyways, a lot of times only one thing's moving. They love to have bullets land in blocks, and so one of them becomes 0, and so you just have the momentum of the bullet before equals the momentum of the block and the bullet afterwards. And then for a bouncy collision, the combined momentum before is equal before and after. So you just have a bunch of MVs. MV plus MV equals MV plus MV. Just watch your signs because sometimes they bounce away from each other, and negatives are super important, or it doesn't work. The center of mass of an object moves so that the total momentum of the body is conserved. So remember how we saw some of the videos and it showed how the momentum stayed at a constant velocity if there's no outside forces, even if everything within the system is moving in a chaotic manner. So it represents the point where all the mass could be placed for an object. We've calculated it. We've played with it. We're going to see it become super important in Chapter 9. But for right now, we just have to be able to calculate it. It can be calculated in the x direction, the y direction. You have to pay attention to positive, negative. You have to pay attention to where you define 0. But there's nothing really complicated about it. It's pretty basic, right? Just the sum of the mx's over the sum of the x. That's simple. All right, so let's look at some sample problems. So we have a roller coaster car and it enters a circular loop portion of the ride. At the very top of the circle where the people in the car are upside down, the speed of the car is 25 meters per second and the acceleration points straight down. It didn't even have to tell us that. You should have known it points straight down. If the diameter of the loop is 50 meters, that's the diameter of the loop. Remember, that's not the radius. And the total mass of the car, plus the passenger, is 1,200 kilograms. Find the magnitude of the normal force exerted by the track at this point. So we're going to draw a track. We're going to draw a car. Always free body diagrams, right? So normal is pointing away from the track. So my normal is going to point this way and gravity is going to point this way. So I can see they're pointing the same direction. So I know that N plus mg, because that's FG, is going to be equal to mv squared over r, because that's centripetal force. And so it's asking me to find the normal force, so I know normal force is equal to mv squared over r minus mg. So we plug in some numbers. Let's move this up just a tad. We plug in some numbers, and n is equal to, we could probably pull the 1,200 out, so we could say 1,200, and then we would have v squared, which was 25 squared over r. Remember, r is not 50, r is 25 over, oh how nice, over 25, minus 10. Oh wow, can we almost do this in our head? 1,200 times 25 minus 10. Well, almost, not quite, because I don't know about you, but I honestly don't know what 1,200 times, because this is 1,200 times 15. So we'll pull out our handy dandy calculator and see if we can calculate that. And it says 1,200 times 15 is 18,000. So that's 18,000 newtons. That's simple, right? Whoa. So normal has to be pretty strong because it has to fight against gravity, right? All right, so that wasn't too bad. And then let's look at the next one. A car, 2,000 kilograms with occupants, starts at the bottom of the hill. It sounds like the same car. That is 8 meters high. If it takes 2 minutes to get to the top, what is the power exerted by the engine if the car coasts down to 3 meters below the peak? What is the speed of the car at this point, assuming it moved? It's moving at 20 meters per second at the top. All right, so we're at the bottom of the hill. So let's draw the hill, and then it's going to come down, it sounds like. All right, so my car starts here. My hill to the top is 8 meters, and it says it takes 2 minutes to get up there. Okay, so we know in my given, let's do this one, practice 5 steps. M is 2,000 kilograms, H is 8 meters, T is 2 times 60, so that's 120 seconds, and we're trying to find power, and so we know that power is equal to, well, some kind of joule on the top. Well, it's going to be potential energy, so mgh over t, and so then when I do my math, I can see that p is equal to 2,000 kilograms times 10 meters per second squared times 8 meters divided by 120 seconds. Oh, these are easy problems. We can handle these. Those are the kind you want to have on your final, right? And some of them will be this easy. 2,000 times 10 times 8 divided by 120 gives us 1333. So this is going to be 1333, sorry, wasn't writing, 1333 watts, right? But then we get a little bit harder problem, and it says if the car goes down to 3 meters below, so my car is going to be right here, so it's 3 meters below the peak. So this is 3 meters, so that means it is 5 meters above the ground. What is the speed of the car at this point, assuming it was 20 meters per second at the top? Okay, so now I got to say, okay, what kind of energy did I have at the top? Well, at the top, it had mgh, and it had 1/2 mv squared, initial. And then at the end, it has mgh, and it has kinetic. Right? And I'm trying to figure out, what am I trying to figure out? What is its speed, right? So I have to find v when it gets down to 5 meters. So when hf equals 5 meters, and v naught was equal to 20 meters per second, and this was h naught, right? Got the idea? So that means we can plug everything in. Well, let's solve first. Please solve before you do things. We're trying to find which V. Oh, I didn't write. It's supposed to be VF, right? So I need to solve for VF. So that means VF is going to be equal to mgh naught plus, because that's the energy I started with, plus 1/2 mv naught squared minus mgh f, because I still have that energy, and then I have to multiply that whole thing by 2, and then I have to divide the whole thing by m. Well, that's cool, because now the m's all cancel, right? So m cancels, right? Because everybody brought mass to the party, and so all the m's go away. So what do we end up with? Let's see here. So we've got VF is equal to 2 times 10 times, well, let's put a bracket around that, 2 times 10 times h naught, which I think was 8, right? Plus 1/2 times 20 squared minus 10 times 5, 10 times 5 squared, right? And bracket. There we go. So let's plug things in. So we've got 2 times 80 plus 20 times 20 is 400. 400 divided by 2 is 200. So that's how much energy I started with, 280 joules, right? Minus 5 times 5 is 25. Plus 10 is 250. And so we end up with 280 minus 250, so that's going to give me times 30, and so it's going to be going faster, which makes sense, so it's now going at 60, that doesn't look like a 60 meters per second when it gets to that part of the hill. All right, nothing really hard, right? Nothing really hard. Okay, a 2,000 kilogram stationary car is hit by a 3,000 kilogram truck moving at 40 meters per second. What is the momentum of the two cars as they stick and slide off together? What is the velocity of the two vehicles stuck together? So we need to find two different things, right? We want to know what the momentum is, what the momentum is of the two cars together and what their velocity is once the two cars are stuck together. So in order to do that, the momentum of the two cars after, right, we know that PF is equal to P naught. So all I got to do is find P naught. And P naught is going to be equal to, well, the stationary car has no momentum, so it's just 3,000 times 40, because that's the only thing moving, so it's 3,000 times 40. Oh, we don't need a calculator, right? Because that's 3 times 4 is 12. How many zeros? 1, 2, 3, 4. So 1, 2, 3, 4 Newton seconds. So it's got 120,000 Newton seconds of momentum, and that's equal to the momentum of the two cars after. So then afterwards I need to find the velocity. So I know that the P is equal to the two M's stuck together, so it's going to be 2,000 plus 3,000, which is 5,000 times V. So that means I just have to take, and this is equal to 120,000, right? So that means that V is simply equal to 120,000 Newton seconds, all divided by, I've got to move this up, all divided by 5,000. I should be able to do that in my head, but I'm not. Kilograms? That was the mass, right? It was just kilograms. Newton seconds. Why does that unit seem to be really weird? But it should work, right? Yeah, it should work because it's right. I don't know why it's just hitting me wrong when I look at it. But yeah, one of the seconds go away, and then one of the kilograms go away, so you're left with meters per second, so that works. So 1,000 divided by 5,000 is 24. So that's equal to 24. Now we go back and use logic. Does it make sense? Does it make sense for it to be moving at 24 meters per second? And we say, well, let's see. Originally it was moving at 40. It gained, right, mass, so yes, it should go down, and it almost doubled, so it makes sense that it went down almost out, but it didn't quite double, so it makes sense. Always go back. Does it make sense? Is it logical? And then we've got, oh, we're not going to do this. Sorry. All right, that's it for the review.